the first time in Korea. And also I apologize for those of you who have seen this talk in Japan. There hasn't been much change in a month. All right, so this is joint work with Damien Caloc in France and my student Junwoo Tu from Madison. So the project we are trying to understand is the following. If Y is a smooth, let's say, projective variety, and X inside Y is a smooth subvariety, let's call this closed embedding I. The question that we are asking is, what can we say, so understand this algebra So I guess to this audience I don't need to explain all that much why this is interesting. If Y was a Calabi-Yau threefold, this OX would be the simplest example of a kind of a brane that is not supported everywhere. And we are trying to understand the space of open string states between the brane and itself, the mirror dual of this would be if we thought about this OX being transformed into a Lagrangian on the mirror, that would be understanding the Floer homology of the corresponding Lagrangian with itself on the other side. So the prototypical case that you would like to think about well, typical maybe in the sense that this is much nicer than the general case, but this we understand very well and we should use as motivation. It's where X embeds inside X cross X by the diagonal map. So in that case, you are trying to compute the X of the diagonal with itself, and that's so X star over X cross X between O delta and O delta is the famous Hochschild cohomology of X. And for this we have very many nice results. So maybe let me say what we know is that this is a commutative ring. This is not trivial. In general, again, to this audience, I don't need to explain, but there is no reason to expect that the X algebra of an object with itself will be commutative. In general, if this were a vector bundle, this would be the endomorphisms of a vector bundle, so no reason to be commutative. This is special in the cohomology, in the Hochschild cohomology case, so it's special for the diagonal. There is a graded vector space isomorphism between Hochschild cohomology of X and direct sum over P plus Q equals to star HP of X wedge Q Tx. This is called the Hochschild-Constant-Rosenberg isomorphism. And thirdly, the Hochschild-Constant-Rosenberg isomorphism, as it was defined in many cases, originally maybe by Gerstenhaber and Schack in this setting, and then by Swan, then by Kontsevich and Kapranov. There are many people who have given this isomorphism. But despite the fact that this is a graded commutative ring, and this is a graded commutative ring, you have ring structures on both sides, the isomorphism doesn't it doesn't preserve the ring structure. However, there's a result of Contae, announced by Contae, but never written down, and then proved by Vandenberg and Kalak. That there is a way to change HKR to get a ring isomorphism. So the point is that this ring and this ring are isomorphic, but not via the HKR isomorphism. So these are the three prototypical results that we would like to understand in the more general setting of the X of a subvariety with itself, not necessarily the diagonal subvariety. And we would like to see how much of this we can recover in the general setting. So I will start with part number 2 of this. And so now in the general case, so for a general embedding of X into Y, let me call it I, so step 2 can be almost generalized, but what the best we can say is there is a spectral sequence which starts with HP of X wedge Q, the normal bundle, and converges to X star on Y between OX and OX. Now, because there's many symplectic geometers in this audience, I would like to point out that somehow this is the canonical definition of Hochschild cohomology as this X algebra. And this side is kind of what you expect to get. The analogous statement for the symplectic side, you'd have here the Hochschild cohomology of the Fukaya category, the Floer homology of the diagonal with itself inside X cross X. And on the right-hand side, you'd have the singular cohomology of the space X. And in good cases, you would expect to have an isomorphism between the Hochschild cohomology of the Hochschild cohomology of the Fukaya category and the singular cohomology, and moreover, you expect also to have it as a ring isomorphism. Well, not quite. It should be the quantum cohomology, but at least this is what you hope. Now, again, in general, for a brane, this left-hand side should be thought of as the analog of the singular cohomology of X, and this should be thought of as the Floer cohomology. And again, the existence of such a spectral sequence is predicted, or it's known, I assume, for every Lagrangian submanifold. But the degeneration of this spectral sequence is a different question. So this part is relatively easy. And I'm going to explain in a second how you get this. So again, maybe to fix notation, N is the normal bundle of X inside Y. And let me maybe give some names. This I will call HT star of X inside Y. And so this is my notation. And this is HH star of X inside Y. So I just use this as convenient notations. I have to warn you that there is a different notion of relative Hochschild cohomology, which is not this, but in the literature. Okay. Now, the question is, what makes the diagonal special, the diagonal embedding special, where we actually can say not only that there's a spectral sequence, but that that spectral sequence degenerates at the E2 stage. So this is the E2 page of the spectral sequence. Maybe I should have said here P plus Q. Why is that the spectral sequence degenerate at the E2 step? So let me show you how you get this spectral sequence first. The way you get it is as follows. You look at this the left-hand side calculation.
Why did you call it Hochschild cohomology? I mean, I can think of that as like natural transformations of the identity of X. Could I think of that as...
No. If you want to think of Hochschild cohomology as some natural transformation, no. It's just because this is an X algebra on the ambient space. If you put Y equals to X cross X and X equals to X...
It's not going to induce natural transformation?
No.
There's a bimodule over X which is coming from like cheese on Y. And you're saying that that thing is...
No, it's not a bimodule. Or...
Okay, I'll ask it.
Y doesn't have two projections to X. We can talk about this, but I don't expect there to be anything of that sort. Okay, so the way to understand this spectral sequence is to notice that the left-hand side is a computation that's done strictly on X. It's a cohomology groups on X. The right-hand side is it's a cohomological calculation on Y. So you'd like to transfer this calculation to X, and that's very easy. So you note that the X algebra on Y between OX and OX is what we think of OX here is really the push forward by I of OX. It's I lower star of OX here. And by adjunction, this is, let me maybe write it as a home in the derived category of X, between the derived pullback by I of I lower star OX and OX. So this is now a calculation entirely on X. I'm going to give this guy a name. I'm going to call it K. And the claim is that what is happening in the diagonal case is that this... Okay, what we know, so the spectral sequence arises from simply it's a hypercohomology spectral sequence. So all you need to do is compute the...
Sorry, so you just told me that actually what you should have written is Hochschild cohomology is actually coefficients in Y. Because Y induces a functor of the derived category of X, which is exactly this push-pull. And you're taking natural transformations between that and the other. Okay, I'll harass you.
We can talk about this. Okay. In any case, so what is easy to prove is to show that this object K of the derived category of X has its ith, its minus ith cohomology sheaf is wedge I of the conormal bundle. So that's easy to show. This is a local calculation, and you just compute with the Koszul resolution. But that only gives you the spectral sequence that I had advertised. So this gives the spectral sequence. However, in the diagonal case, things are much better. Namely, this object K is formal. So K is isomorphic to direct sum over I, wedge I, and dual shifted by I. So note that in the diagonal case, the normal bundle is just a tangent bundle. So that is a cotangent. The normal bundle is a tangent bundle. So that's why you get the tangent bundle here as opposed to the normal bundle there. So you get exactly this. So what I'm saying is that what's special in the diagonal case is that not only does this complex have these sheaves as its cohomology, it actually is quasi-isomorphic to the complex which has just these sheaves and zero differentials. So by this I mean complex with 0 differentials. Okay? And this gives, once you know this, the hypercohomology spectral sequence completely degenerates at the E2 stage, and you get a direct sum decomposition. So I'm not going to give you the proof of this, but I'm going to tell you the first result. Which tells you exactly for what kind of closed embeddings this actually happens. We have, this is a theorem by Dima, Rinkin, and myself, which says the object I upper star, I lower star OX in dB of x is formal, i.e. I upper star, I lower star OX is isomorphic to direct sum wedge I and dual shifted by I. Too many I's. Sorry. If and only if the normal bundle N extends to a vector bundle on the first infinitesimal neighborhood of x inside Y. So let me explain this. On x you have this vector bundle, N. Now, you can look at the first infinitesimal neighborhood of x inside Y, which means you take the ideal sheaf of x, you square it, and you look at the nilpotent scheme cut out by I squared. That's another scheme. You always have an embedding. So there is always an embedding of x inside x1. And I have a vector bundle here, N, and I ask, is there a vector bundle here which pulls back to my normal bundle here? Okay? Now, note that, so let me state a few special cases of this, special applications of this. So let me maybe call this condition star. So first of all, I would like to say the following thing. Star is implied by the following thing. The short exact sequence Tx, Ty restricted to x, n splits. So if you have you always have this short exact sequence of vector bundles on x. If this short exact sequence splits, in other words, the tangent bundle of y restricted to x is a direct sum of Tx and n, then condition star holds. In fact, in that case, every vector bundle on x extends to a vector bundle on x1. And this in particular, for example, is implied by the case where if G finite acts on y and x equals to yg, the fixed locus, then the tangent bundle exact sequence splits. Because if you give me a tangent vector to y at the fixed point of the action, then you can always average it through all the possible translates by g, and that will be a tangent vector to the fixed locus. So that gives you a map going back that way. So in particular, this is implied by the case where x is the fixed locus of an involution, which many people here have talked about. There was Jake's talk and Professor Ota's talk and so on. All right. So this is So all these implications are strict. You don't need any one of those to actually get that to be split. This is the strong condition. I have to mention that after giving talks about this, Pierre Shapira told me that he had some notes from 1993 of Kashiwara, a letter that they exchanged that was never made public, which showed, so Kashiwara had this result. The implication that if this holds, then this holds. So he knew that if this exact sequence splits, then this object is formal, and then you get the degeneration of the spectral sequence. So this was independently. Okay, now this takes care of the analog of result 2 for Hochschild cohomology. It gives you a spectral. So okay, sorry, maybe I didn't say, but so therefore, if star holds, HH star of x over y is isomorphic to HT star of x over y as vector spaces, as graded vector spaces. So we get an analog of Hochschild-Constant-Rosenberg isomorphism. Okay, this generalizes condition 2 that we had. This is the thing that we want to compute, and this gives you a vector space isomorphism, what it actually is. All right, now let's move on to questions about the ring structure. Now, HT star again. HT star is direct sum p plus q equals to star HP of x wedge q normal bundle. Okay? And this was the X algebra that we were interested in. Now you look at this theorem now, and you realize that there's no hope to generalize part 3 as such. The main reason being that the right-hand side will always be graded commutative. This is a graded commutative ring. But on the other hand, the left-hand side, the X algebra, has no reason to be graded commutative. In the case of Hochschild cohomology, this was a bit of a miracle that Hochschild cohomology is always graded commutative. But in general, there's no reason to expect that. So maybe let me state, just so that while I still have everybody's attention, let me state the theorem that, well, the conjecture that we want to make. And I will say more about what other general statements we can prove. But here is the conjecture, so that, and at the moment it will seem completely unmotivated, but this will be the, this is the main conjecture that we can make at this point. The claim is the following. We have to assume that this condition holds. So let me call this condition that the tangent bundle exact sequence splits. This is a conjecture. If star star holds, then this ring, HT star of x over y, has a richer structure. The cohomology of the exterior powers of the normal bundle has a Lie algebra structure as well. Which makes it into a Poisson algebra. And the center of the relative Hochschild cohomology is isomorphic to the Poisson center of HT star. So we are not, and maybe let me say as rings. So let me say, so this would completely recover Kontsevich and the Vandenberg-Kalak theorem. In the case of the diagonal, this Lie algebra structure is trivial. This ring is commutative. And there is no Poisson center because the Lie algebra structure is trivial. So you get that Hochschild cohomology is isomorphic to polyvector field cohomology. So this generalizes the results of Vandenberg and Kalak based on Kontsevich's prediction. So again, I have to emphasize that this isomorphism, just like in the Kontsevich result, is not the isomorphism that you have from this theorem. It's a corrected isomorphism. It needs to be corrected. So now let me briefly review, well, maybe let me say what the Poisson algebra is, because maybe not many people here are interested in that. Poisson algebra is just something that is a commutative ring together with a Lie bracket, such that the Lie bracket is a derivation in each one of the variables. It's just a natural thing. Many people might have seen here the Gerstenhaber algebra structure. A Poisson algebra is like a Gerstenhaber algebra, except that the bracket in the Poisson algebra has the same degree as the multiplication. It's homogeneous. It doesn't shift degree. Okay, so just maybe to elucidate the differences.
Reason to assume double star instead of single star?
You'll see in a moment why we assume double star. That's a very natural assumption from the point of view of Lie theory. This conjecture has the basis for this conjecture is entirely coming from Lie theory, and the natural assumption is that of double star. We don't know how to, at least nobody in Lie theory has seen condition star, basically. And we don't know any counterexamples, obviously, but that's a very natural assumption to make. So what is the Poisson center? So it's called HP0 is just the Poisson center. The Poisson center is just the kind of thing, the things that commute with the bracket. Which bracket to 0 with everything else. So maybe let me give one example that you should think of as a prototypical example of a Poisson algebra and of such a picture. So to keep in the back of your mind, what you should think of is the following. If G is a Lie algebra, then you can take the symmetric algebra on G. So you just take like the polynomial ring on that Lie algebra. This is a Poisson algebra. By taking the bracket, the original bracket that we have on G, and extending it to be a biderivation on SG. There is only one canonical way to do that. And then the Poisson center of SG is isomorphic to the center of the universal enveloping algebra of G. So you should really think of this as a little bit analogous to the symmetric algebra on G with its Poisson structure, and of this as UG. Okay? This is non-commutative just like UG is, but the center of it is the same as the Poisson center. Maybe Okay. The analogy is not perfect, and you'll see why, but it's for the moment just as good. So now let me explain the basis for this conjecture. And to explain this, I need to go back and explain Contaevich's understanding, Contaevich's idea to prove this for the diagonal embedding. So here was his idea. He said, we've already seen that the Hochschild cohomology of X, which was X over X cross X between O delta and O delta, we've seen that this is isomorphic to hom on X between delta upper star of O delta and OX. This is exactly what I wrote before. And this was the crucial object K that we were interested in. What Contaevich was able to, what you can see actually, now that Contaevich has pointed this out to us, it's not very hard to see. So K is a commutative Hopf algebra object in dB of X. So what does that mean? That means that it comes with natural maps. It has some map like this, K tensor K to K. It comes with another natural map from K to K tensor K. It has some maps from OX to K and from K to OX, such that when you write down the usual conditions for something to be an associative algebra, using this as a multiplication and this as a unit, or a co-associative coalgebra, using this as co-multiplication and this as co-unit, and write down all the compatibilities, to have a Hopf algebra, you have that all those properties.
Shouldn't I be worried because you try to do this in the derived category where equality is a subtle notion? I mean, you know, if you have a Hopf algebra...
No, equality of morphisms is equality of morphisms. The derived category is a category. Okay? All that I'm saying is that if I take a morphism like this, there are two morphisms here, identity tensor mu and mu tensor the identity, to K tensor K, and then I go to K by mu. I'm saying that the two compositions are equal, and equality of morphisms is perfectly defined in a category. I'm not having a two category or anything fancier than that. Okay. Now, commutative Hopf algebras are very nicely classified with one extra condition which holds here. So there is a theorem called the Milnor-Moore theorem, which tells us that if K is a, maybe let me write the dual statement. If K dual is a co-commutative, so the dual of that will be a co-commutative Hopf algebra, and satisfying some technical condition called connected. I'm not going to say what that means. Hopf algebra, then K dual is isomorphic to UG for some G. So we know exactly that this K, more precisely its dual, should be exactly like the universal enveloping algebra for a Lie algebra. So it should satisfy all the nice properties that the universal enveloping algebra of something should be. And in fact, this was proven by Kapranov based on this suggestion of Kontsevich, and more recently by Roberts and Willerton. They wrote down all the careful details. And sorry, I should mention also Markarian. Yeah. Indeed, the dual of delta upper star of O delta is isomorphic to the universal enveloping algebra on G. I'll say in a second what G is. And every E in dB of x is a module over G. So not only do we find this remarkable Lie algebra in the derived category of x, of any x, moreover, every object of the derived category is canonically a representation of G. So we should no longer think of the derived category of x as just modules over, kind of the category of modules over a ring. We should think about it as the category of representations of a Lie algebra.
So how can I understand this isomorphism between algebra and
Sorry? Between what? This one? Well, what I'm saying is this one has got a Hopf algebra structure. I just explained that it has. No, it's an algebra object in a monoidal category. You can define the notion of an algebra whenever you have a tensor product. You can define the notion of an algebra, namely some object in your category having maps like this, satisfying some compatibility properties. Okay? And algebras in vector spaces are your usual notion of algebra, but you can have algebras in other categories.
Sorry, so what's this Lie algebra G?
Okay, and now here's what G is.
Is it again a Lie algebra object in the category of the derived category?
Yes, yes. So G is the tangent bundle of x shifted by -1 with the Attea class as bracket. So what does that mean? It means that it comes with maps, with a map from G tensor G to G. This is the Attea class, which I should think of as a bracket, satisfying some properties. If I interchange the two factors here, the map gets a minus sign. If I write 3 of these and write down the usual Jacobi identity, I get the Jacobi identity. Okay? So you just formally write, you can define a Lie algebra object in any monoidal category, a commutative algebra, anything that you want can be done in a monoidal category. I'm not going to say what Attea class is. It's a very basic construction. But let me maybe say that Attea class of any vector bundle or any object of the derived category, it's a map. Usually people think about it, for those of you who know what this is, you think about this as a class in H1 of x with values in endomorphisms of E tensor omega. This is the obstruction to the existence of a connection, of a holomorphic connection on E. But another way to write it, so alternatively, and this is the way we like to write it, it's a map from Tx shifted by -1 tensor E with values in E. If you unwind what this thing says, it's exactly this. The H1 corresponds to the shift by -1 here. This Tx, if you put it on the other side, becomes an omega. You have an E here and an E here that gives you the endomorphisms of E. Okay? And the way you should think about this is just a map G tensor E to E, which makes E into a representation of G. Okay? if you had the usual representation and the usual Lie algebra and the usual representation, you have a map from G tensor E to E, which encodes the representation. This is exactly it. Okay? So now, what... I shouldn't have deleted this. This was Hochschild cohomology of X. Now, here is what Kontsevich said. We have this is now the universal enveloping algebra of G. What is OX? Well, OX, we know that it has trivial Attea class because it admits a connection. So the Lie algebra structure map is 0. And so this should be the trivial representation. So we should think about Hochschild cohomology of X. I remind you that this is UG dual. So moving the dual to the other side, it's home from, in the category of G representations between the trivial representation and UG, if just dualized. But taking homomorphisms from the trivial representation into any representation just gives you the invariance. This is the G invariance of UG. Okay? And now this was the major insight, and this is where the word Duflo comes into the picture, is that there is a famous theorem of Duflo that this is by Duflo. This is a theorem, is that the G invariants of UG are isomorphic to the G invariants of SG as rings. But after not using the usual Poincaré-Birkhoff-Witt isomorphism, there is a vector space isomorphism between here and here, the Poincaré-Birkhoff-Witt. But that doesn't work. You have to correct it. So this was the basis of Kontsevich suggesting that if you take the Hochschild-Constant-Rosenberg isomorphism and correct it, you get an isomorphism between this, and this can be immediately identified with this HT star of X, the polyvector field homology. So the point was that you reinterpret Hochschild cohomology as something in Lie theory, and then use a classic result in Lie theory to classic 1990s, not so classic, and reinterpret everything in terms of Lie theory to get the result that you want. So now I'm going to try to do the same exact thing for the more general case of an arbitrary closed embedding. And let me tell you what the dictionary is. So I'm going to try to build a dictionary now. Between varieties and Lie theory. So let me get to this dictionary. So in the previous case we had just one space X. So now we need two spaces. So we have two spaces X and Y. On the other hand, we have two Lie algebras. Let's call them H, which is Tx shifted by -1, and G, which is Ty restricted to X shifted by -1. Each one with its own Attea class. So this comes with the Attea class of X. This comes with the Attea class of Y restricted to X. Okay? Here we had a map from X to Y, which itself gave rise to a map. The tangent bundle of X includes into the tangent bundle of Y. So it's natural to see that, say that H includes inside G. And in fact, it's very easy to see that the Attea, if you look at properties of the Attea class, you should see that the Attea class of y, when restricted to Tx, gives you the Attea class of x. So this gives you a map of Lie algebras. Now, how should we think of the fact, if I have an object on y, I can always restrict it to x. E in dB of y can be mapped to E restricted to x in dB of x. How should I think about that? Well, I told you that objects in the derived category of y were representations for G. So I should think about this as E in rep G becomes the restriction of like the analogous thing to restriction of scalars. If E is a representation for G, it's automatically a representation for H. Restriction from G to H of E in rep H. So if you give me a G representation, I can always turn it into an H representation in the obvious way. And this is again the statement that the Attea class of E restricts to the Attea class of if you take the Attea class of E restricted to X, it's the Attea class of E restricted to X. This is the usual, maybe I should have said, the Attea class is the way to define Chern classes. And this statement is nothing but the statement that Chern classes pull back well under any morphism. Okay? Other things in our language, we have OX and OY. Well, these correspond, as I told you, that this is a trivial representation for G, the trivial representation for H. Sorry, the other way around. Now, let's do something a little bit more fancy. How about take something from Lie theory? Whenever you have a map of Lie algebras, not only can we restrict G modules to H modules, we can induce representations from H modules to G modules. So if I look at the induction functor from rep G, it's from rep H to rep G. How should I think about this? Well, the natural way to do it is to think about it functorially. The induction functor is the left adjoint to the restriction functor. The restriction functor was the restriction functor from here. So the correct thing is to take the left adjoint of the pullback, which is this I lower shriek functor from dB of x to dB of y. Okay? And now we can finally understand, since we've done all the language translations, this is the useful thing. How about let's try to understand this object I lower shriek I upper star of OX. You should not worry don't worry about the fact that this is lower shriek. This is very oops, sorry, the other way around. I upper star I lower shriek OX. This is the object. This is very analogous to I upper star I lower star OX, the object K that we wanted. In fact, you can immediately see that this is the same thing as K dual. So what does this correspond to in this dictionary? What we are doing is we're going to do first induction and then restriction on the trivial representation. On 1H. And this is a very easy calculation to do in Lie theory. This turns out to be UG mod HUG. So you take the universal enveloping algebra of G and mod out by the left ideal generated by H. So this is the dictionary. Oh, maybe let me not stop here. In this language, moreover, the relative Hochschild cohomology of x over y, which was hom on x between OX and K dual, this turns out to be exactly hom in H representation between the trivial representation of H and K dual, which was UG mod HUG, which is exactly, I told you that homomorphisms from the trivial representation are just the invariants. It's UG mod HUG dual. Sorry, H invariance. Now, we also had on the left-hand side this HT star of x over y, which is just a cohomology of the symmetric algebra on G mod H. Sorry, on the normal, maybe let me say it like this. On the normal bundle shifted by 1, by -1. And that corresponds on the left-hand side to SG mod HSG H. And the point was, we were trying to understand in the derived category world, relate this ring to this ring. So in the representation theory world, we are asking, does anybody know any relationship between this ring and this ring? And you go to a Lie theorist, and they say, yes, this is a conjecture of Duflo. So the generalized Duflo conjecture, which many people say it's very close to being proved, but not quite yet. Which says the following: if the map H to G is split as a map of H modules, then there is a ring isomorphism between the center of UG mod HUG H and the Poisson center of SG mod HSG H. Okay? So you take this generalized Duflo conjecture and use the translation that I have just provided for you here, this dictionary, and you get exactly the conjecture that I stated. It says there must be a Lie algebra structure here, which makes this into a Poisson algebra, and the center of the Duflo of this ring is the Poisson center of this ring. Now let me maybe explain the basis. It's relatively easy to explain the basis for the generalized Duflo conjecture. The generalized Duflo conjecture comes from the following basic idea. It says, this is a general principle in quantization. It says the following: if you start with a commutative ring and the Poisson structure on it, just like the symmetric algebra with the bracket given by the bracket from the Lie algebra, there are various procedures to quantize this ring. So to turn it into a non-commutative ring in the direction of that Poisson bracket. The conjecture, the meta principle, says that the center of the deformed algebra should stay the same everywhere, except that in the case of the original commutative algebra, you should not think of it as a center, but the center of the Poisson the structure. So in this case, this is a quantization of this. So if you look at this ring, it is a Poisson algebra. This turns out to be a quantization exactly in the direction of that Poisson bracket. And so the center should be the Poisson center. Now let me tell you what we can prove of this conjecture that I stated, and with this I will finish. By the way, maybe while I erase this dictionary, I would like to say some curious facts. These are not, I don't have strong mathematical evidence for this, but I have strong kind of hopeful evidence. One remarkable thing is that the existence of this dictionary should be related to the existence of a certain 1 plus 1 plus an extended three-dimensional full, whatever these are called, topological field theories in the sense of Lurie. So extended topological field theory that associates stuff to points, circles, points, one manifolds, two manifolds, three manifolds. And that should explain the existence of this dictionary between spaces and Lie theory. So now let me just tell you the statements that we can actually prove. Sorry. So what we can prove, so theorems. First of all, ht star of x over y has a Lie structure, a Poisson structure, when star star holds. So that's relatively easy, although a little bit unexpected. You don't quite see a priori that should have a Lie algebra structure. The second step is it's a theorem. Namely, we can prove, so the generalized Duflo conjecture actually is known to hold in the case, in what's known as the involutive case, namely when H is the invariant part of an involution, not an arbitrary group action, an involution acting on G. So if there exists if there is a Z2, Z mod 2Z action on Y such that x equals the fixed locus, the conjecture holds. In fact, it holds much stronger. Namely, HH star of x over y is commutative, and HH star is isomorphic to HT star. So this generalizes Koncevich's result, because if you think about it, the diagonal is exactly the fixed locus of an involution, of the involution which interchanges the two factors. This is what we can prove. I think we are very close to proving, so I think I can claim it. I can follow in the footsteps of Koncevich and call it a claim and not a theorem. Claim: if X is a generalized complete intersection in Y, i.e. there exists a vector bundle E of rank equals codimension of X in Y, and a section which cuts out seems theoretically. Then again, HH star is commutative, and HH star is isomorphic to HT star. And I think that's all the results that I have. I would be very curious. So this result looks a lot like the results that Jake and Professor Ota mentioned, that if you have the fixed locus of an involution, everything goes on exactly, all the best results that you can hope for hold. It seems like there is another analogous situation in algebraic geometry for which we can prove this, and it would be interesting to find out if there is anything similar to this in symplectic geometry. Thank you very much.